Hello, my name is Marco Sarafini, and I'm an assistant professor at CICS. I lead the data systems group. Let me tell you more about the research of my group. So the research areas of my group are at the intersection of systems and data. So we look at issues such as performance, scale, usability, and programming abstractions in the context of graph data management, graph data analytics, and machine learning, and combinations of these two areas. Let me tell you, for example, about one area I work with my students, which is machine learning on graphs. But before I go there, why focus on graphs? Well, graphs are a universal formalism to represent all situations where, all data sets where we want to extract information, not just from single entities, but also from their relationships. And there are many use cases where you want to do that, from relational data to security to recommendations and social networks, NLP. So what you do in this case is you extract a graph from your data, the graph structure. And sometimes when you do that, you integrate multiple data sources, and then you obtain a graph which you can use for further analysis. It's a very flexible formalism. Machine learning on graphs in particular is becoming increasingly popular in many applications, such as search, Q&A, semantic web, where you have a knowledge base and you want to integrate deduction from this knowledge base with induction from text, information that you extract from the text, and also personalization and recommendations. So for example, if you have, you could have a graph that represents users, their relationships, whether they buy or they like certain products and how products are connected with each other. And then you can use this information to recommend products to users. So one important intermediate step when you perform machine learning is representation learning. So instead of coming up with features yourself, it's often better to use a neural network to find the features of the relevant features of data, which may be hidden. For example, in natural language processing, it's very common to extract embeddings for words. So each word is assigned an n-dimensional vector, which is called embedding, and this n-dimensional vector encodes the hidden features, which sometimes can have a semantic meaning, right? So we can use vector algebra to find interesting relationships between the meanings of the words. And once we find, so in order to find these word embeddings, we train a deep neural network. Once we have these embeddings, we can use them in downstream tasks like named entity recognition. Now you can do something similar for graphs, where now you typically learn features for vertices. The difference here is that instead of learning these features from, like in the case of text, you learn features from other words that are close by to the word you're learning the embedding for in sentences. In graph neural networks or in graph representation learning, you want to learn the properties of one vertex from its neighborhood. So it could be one hop, two hop neighborhood from random walks, and in general from the graph. And then again, once you have these embeddings, you can use them for some downstream task. Now, in the context of graph machine learning, actually, graph neural networks are an interesting emerging architecture of neural networks, which you can see as an evolution, yet another important class of neural network architectures, which is tailored for graphs, just like convolutional neural networks, for example, are tailored for images, or recurrent neural networks are tailored for text, natural language, and sequential data. The big difference here, though, is that unlike for RNNs and CNNs, with graphs, data correlation does not imply data locality. So In graph neural networks, the idea is that we obtain the features of a vertex by aggregating the features of the k-hop neighbors of the vertex. And at every step of aggregation, each vertex aggregates from its neighbors using neural network layer. Now, the problem here is that this neighbor-based aggregation performs a lot of random accesses, right? Because I need to get neighbors from different memory locations, and this becomes an important bottleneck. So this aggregation is an important performance bottleneck that does not arise in other architectures. Another problem that arises on graphs is how to use mini-batching. So in mini-batches are a sample of a subset of the input data that we use for one training iteration. And typically, when you have data sets that are discrete, you can simply pick different points in your data set independently and form mini batches that way. But in graphs, it's different because as an input, you get one single graph, and now you need to extract mini batches from it. And the way you do that is by sampling the graph, for example, sampling the k-hop neighborhood of a subset of the vertices. And there is a growing literature on how to perform this sampling. So there are different algorithms with different properties. The challenge here is that actually graph sampling algorithms do not leverage the GPU. So the typical approach is to run sampling on the CPU. Then because of this random access, like before, by doing graph sampling requires a lot of random accesses. So people do typically random sampling on the CPU, and then once they obtain the mini batches that way, they can actually run the training on the GPU. The problem is that doing that makes sampling become an important bottleneck. So we have measured that it could take up to 62% of the total training time if we use one GPU, and if we have a system, a node with multiple GPUs, the CPU, the one CPU is going to become even more of a bottleneck. So my research group actually is looking into several issues related to get systems for graph neural network training. So we have just completed work on a project called Nextdoor, which significantly speeds up sampling using GPUs. And the idea is to both provide programming abstractions, so an API to hide the complexity of GPU programming, while at the same time offering the machine learning experts the possibility of implementing their own sampling algorithm, while at the same time providing much better performance than any CPU or GPU-based implementation that exists. And that's thanks to a new approach to parallelism that is specific to sampling. And for example, in the slide, you can see how easy it is, for example, to implement 2-hop sampling using Nextdoor, just a few lines of code, and you get a very efficient implementation. Ongoing work from my group is on speeding up distributed sampling and training. So very often, actually, graph neural networks are run on large graphs that don't fit in memory of a single machine or a single GPU, even less so. So how to actually distribute the sampling and the training, in particular, since now with Nextdoor, we have enabled running sampling efficiently on the GPU, how do we actually schedule the GPU resources, and how do we coordinate this process when we get even less data locality because we might have to fetch data from different sources. And also we are working on speeding up graph neural network trainings on GPUs, not just the sampling process, but also the training. And the idea here is to increase GPU utilization by using techniques like operator fusion and resource scheduling. Now, another big area from my group is querying and storing graphs. So in previous work, I have worked on graph mining applications like frequency graph mining and motif counting. And I have developed Arabesque, which was the first general system for graph mining. Basically, you can think of it as a MapReduce for graph mining. You could run graph mining with a simple API or a distributed system. and very efficiently. So today there have been several follow-up works on graph mining that have built on the experience of Arabesque. So what is the next step, the next problems? So a recent survey from users of graph tools have highlighted some important pressing needs and ways ahead for this type of system. So first of all, it has shown that many users have to deal with large graphs, that these graphs are dynamic, so they change over time, that they are stored on a distributed system. And actually, there are many applications that are latency sensitive. So we want to run graph analysis fast. The faster we run it, the better. And as central concerns for these users, people have mentioned scalability and performance. So for example, examples of applications with these characteristics are, for example, recommendations and question answering. So companies like Alibaba and Amazon and Pinterest, they use actually graphs for recommendation and question answering. And in some cases, actually, they need to query the graph with very low latency. A similar example is when we run fraud detection and companies financial institutions that run fraud detection or even online stores, and they have a graph of financial transactions and they need to detect patterns in this graph that denote potential frauds. So in my lab actually is working at different layers of this stack. So in previous work I have worked on transactional storage. So how to build a storage system that is able to accept dynamic updates while providing similar performance as read-only, read-optimized storage. Current work is actually on running distributed graph queries with strict latency bounds. So you can reduce the latency of a query, especially in graph queries where queries need to hop potentially from one server to another and perform multiple hops. You can use replication to minimize these hops. However, you want to replicate as little as possible in order to achieve your goals, your latency goals. So one of my research projects of my students is coming up with algorithms to replicate data in an efficient manner. And finally, another project is actually online indexing for graph queries. So because graph queries are so computationally intensive, people have looked into using hardware level features like CPU vectorization to speed up the process. And typically one way to do that is to index the input graph in a format that is friendly to vectorization. However, this is very expensive. So we are in one project, one paper that is currently under submission. We are looking into how to actually speed up this process by doing indexing online, not as a preprocessing step, but during query execution. And that's actually much more easy to run when you have dynamic data, and preprocessing might be unfeasible. So finally, one last area that I'm working on is data management for machine learning. And as we have discussed, a common machine learning pipeline is to first learn the representation of your data, come up with some embeddings, and then run some downstream task. Now, the one important issue in terms of systems for machine learning is how to store these embeddings and retrieve them efficiently. So some of my students are looking into how to index embeddings, how to store them efficiently, how to integrate an embedding storage system with existing ML machine learning pipelines, how to enable transactional updates, multi-versioning while providing efficient access. And in particular, right now, the focus is on running nearest neighbors efficiently on large data sets of embeddings. That's it. I would like to thank my wonderful students for all this research that I have briefly discussed, and the sponsors of my research. Thank you very much.